Hi, everyone, and welcome. Aaron Smith and Nancy Bakeman with EBA. Gearing up for the summit. Looking forward to see a lot of you there. And Brian is in Phoenix. We're excited to welcome Brian von Allworden. Brian is a professional engineer and senior project manager and SIP expert with Wright Engineers down in Phoenix. We're excited to welcome him to the EBA webinar podcast series. And we will be taking questions throughout today's presentation. Just enter your questions in the Q&A section or the chat section, and I will ask those to Brian. Brian, with that, I'll turn it over to you and welcome.
Thank you, guys. Yes, I am Brian von Allworden, and I am a structural engineer with Wright Engineers. Over the past 25 years or so, my main focus has been on structural insulated panels, or SIPs. And during that time, I've designed, engineered, and built a couple hundred SIP projects. Everything from low-cost living communities to 4- and 5-story apartment complexes. I'm also a member of SIPA and helped write the National Design Guide for the design of SIPs. And for the past 15 years, I've lived in my own SIP home. Now, structural insulated panels can make a very efficient and affordable environmental envelope, but only if you design them and build them correctly. So today we'll be looking at some of the do's and don'ts of SIP design and construction. But first, I think I want to look at a little bit of history. A lot of people think SIPs were new building product, but the truth is the SIPs are designed originally back in 1935. Since then, SIPs have evolved to what we're using today. And a couple of the big advances, one was in the 1960s when they came about with expanded polystyrene, or EPS. And then in the 1980s, when they started developing oriented strand board, or OSB. Now, SIPs replace conventional framing. So they can hold gravity loads, transverse loads, and shear loads. But they also provide an environmental envelope far superior to that of conventional framing. And they also create much straighter walls. SIPs also take about 25% of the time to erect than conventional framing. So let's look at a SIP. SIP, obviously, structural insulated panel, consists of two skins that are laminated to an insulated core. Now, the skins can be OSB, plywood, magboard, steel, or even drywall. The most common SIP, and the one we're going to be discussing today, has oriented strand board skins and an expanded polystyrene core. So SIPs start with that expanded polystyrene core. And that core is a thickness of a 2-by-dimensional lumber. So it's 3.5, 5.5, 7.25, 9.25, or 11.25 inches thick. This is so that you can use standard dimensional lumber for the sill plates, the top plates, and the bucks. Now, this core is then pressure laminated with the skin, in this case, oriented strand board. Typically 7/16 oriented strand board, but you can use 5/8 or 3/4 if it's required for fire or for structural reasons. Now, SIPs come in either 4 or 8 foot wide, and vertically they're usually 8, 9, 10, 12, 14, 16, 18, 20, 22, and 24 feet high. This is quite a large panel compared to our little person there. But the most interesting thing about this panel is the skins are a single piece of OSB. There's no joints on the surface of this panel. Now, you can also take this panel and lay it down. If you want an 8-foot plate height, you can lay this down and install a 24-foot long wall in about 15 minutes. It also eliminates about 2/3 of your vertical joints. Let's look at how these all go together. When you do SIPs, you start in a corner and then you work your way around the building. The panels are connected using splines vertically between the panels. Windows and doors can be nothing more but a hole in the wall, or they can be built up and they can use either a header above or window fill below to create the opening. Now, this illustration shows a flat top plate, but that's not always the case. You can actually rake the panels at the gable ends, so you have a complete environmental envelope from the ground all the way to the roof. Instead of adding a gable truss or a pony truss on top of an 8-foot plate, which creates a hinge effect and cracking of your exterior finishes and doesn't create that environmental envelope we're looking for. The roof is placed on the supporting members. Now, they're structural and they can span up to 24 feet. But for economic reasons, a good rule of thumb is about 16 feet. Now, the SIP roofs are also good for cantilevers, both double cantilevers and single cantilevers. But now let's move on to what we really want to talk about, the environmental envelope. There are two ways energy is lost through the shell of a building. The first is through what we call conduction. This is energy passing directly through the material, the walls, the windows, the doors. The other is called infiltration, and this is air movement. Now, the hot air carries energy through the walls, and so that's called infiltration. That's the second half of the equation. Let's start by looking at conduction, though. There are two ways to control the flow of energy through a wall. The first is what's called thermal mass. This is when we take a very wide material that's very low in its R value. So now we can get energy actually moving through the wall, but it's very wide. So it takes a while for that energy to get through. So during the summer days when it's hot outside and cold inside, that energy will move towards the inside of the building. But then when night comes around and it gets colder outside than inside, the energy will turn around and start going back to the cold area. And that's called a flywheel effect. The other way to control energy passing through the wall is to create just a barrier. So now you have energy that we try to stop from even getting in the wall. Now, obviously, we can't stop all the energy, but if we use a very high R value material, then we can stop a lot of that energy from getting into the building. SIPs are an energy barrier. So that's the type of system we will be using with SIPs to stop the energy flow. So conduction is energy moving from one molecule inside the substance to the other molecule through direct contact. And the more dense the material is, the faster that energy moves. And we use what's called an R value or a resistance number that tells us how fast that energy moves through the material. This is a list of R values for standard construction materials. So you can see steel basically has no resistance. Energy gets there and just flies right through. Framing lumber has a resistance of about 1.25 per inch. And EPS, which is the interior core of the SIP, has a resistance value of 3.6 per inch, which is about 3 times that of framing lumber. Now you got to remember, R value for material is one thing, but what we really want to talk about is the true R value. This is the R value of the wall. This is the R value of all the pieces put together and how they're put together. And then you have to figure out exactly how the energy is going to flow through that wall, and that creates the true R value of the wall. Now, 6-inch SIPs have an R value of 23. A 2x6 stud with bad insulation is less than 15. And if you replace that bad insulation with foam insulation, you're less than 18. And there's a reason for that. It's called thermal bridging. This occurs when there's a low R value material that goes from the interior to the exterior of the building, someplace where the energy can actually go through the wall or bridge all the other material and get inside. Let's look at an example. Here's a SIP wall. and a stick wall. If we look at energy attacking that SIP wall, it has to go through that EPS, that 3.6 R value material per inch, and try to get into the building. So not a lot of it makes it. But if we look at a stick wall, you can see the energy doesn't go through the insulation, but it combines and goes through those studs. And those studs are the thermal bridging in a stick wall. So you get a lot more energy going into the wall than if you use the SIP wall. Now, SIPs can significantly reduce conduction because they don't have that thermal bridging. The other half of the equation is infiltration, air moving through the walls, through the gaps. When you turn on your air conditioner, your furnace, whatever creates your air in your house, it creates a pressure. So it's trying to push all that air outside through the walls. And so any gaps or air movement you have through those walls is costing you money because it's costing you to heat or cool that air and you're just throwing it outside. So the tighter the structure, the less energy that gets out. Now, SIPs are very tight, so they can significantly reduce infiltration on a house. So when we build with SIPs or anything else, we need to keep two things in mind as far as our environmental envelope is concerned. First, we have to make sure we keep our thermal bridging to a minimum. And then the second part is we have to stop any air movement through the walls themselves. So let's look at some details and see how we can do this. Starting at the foundation, we start with an anchor bolt like any other project. But remember, SIPs has a taller sill plate because of a capillary break. So you have to make sure your anchor bolts are sticking out 3.5 inches. Typically, they stick out 2.5 inches. And good concrete guys that stab in these anchor bolts, they can put them exactly where they need to be, but they put them 2.5 inches sticking up because that's what they're used to. So you got to make sure they're sticking up because you cannot go in and drill out your sill plate to put your nut and washer in. On top of that, you need to put a seal or a sealant down to stop any air going between your concrete and your capillary break. In our case, the capillary break is a 3/4 inch treated piece of CDX plywood. Now we use a 3/4 inch pressure treated because if you use a 1.5 inch pressure treated, it's just more thermal bridging. Then we take a bead of sealant, a real nice big bead of sealant, and put it on the exterior side of that anchor bolt. That will allow no moisture to come in from the outside and get to that anchor bolt and corrosion. On top of that, we put a non-pressure treated 2x seal. Now this is important because nails that get driven into pressure treated lumber corrode after about a year. So we want to try to eliminate as much pressure treated lumber as possible. So we don't have to worry about corroded nails or changing our nails out in our guns. And pressure treated nails are more expensive. So we use a non-pressure treated 2x seal plate. Then we come in and we put our washer and our nut on and we tighten those down, and we want that sealant to spread out and fill up all the gaps. When you put that sealant on, it's kind of fluid. It's not liquid, but it's kind of fluid. And so you put it on and you can squeeze it out. After about 15 minutes or so, it becomes more rubbery. So it doesn't squeeze out. So you need to close off your connections as you go to make sure that sealant gets where it needs to go. If it rubberizes, you can't seal it. We put a couple more beads of sealant on top of the sill plate to keep air from going around that sill plate and through the SIP to the other side. And once we get this SIP up, we want to nail it. Once again, we want to nail it off right away to make sure that that sealant gets to where it needs to go and doesn't rubberize before we seal it off. Now you'll notice we use sealant in 3 places on this sill plate. So we want to make sure no air gets through that at all. However, we do have thermal bridging. And that thermal bridging is caused by 2x sill plate and the 3/4 inch pressure treated. We can't get away from that. We need that structurally. Now let's look at the top plate. The top of the wall has a single top plate. In conventional framing, you have a double top plate because you have forces. You got shears going through that double top plate. So you need two of them, and you need to lap them, put a lot of nails in to put them together. SIPs are known as a stress skin panel, meaning that all the forces are in the skins, not in that top plate. So we don't need to lap the top plate. We just need to use one single top plate to allow us to get the nails in. Now, sometimes you've got shear walls that have to support a lot of lateral load, and those require more nails. So we use a 4x, not because the 4x takes more stress, but because we need more area just to put in our nails. We use 2 beads of sealant on top of the plate because most of the time there are chases in the panel that go all the way up through the foam. And those chases connect to horizontal chases that connect to other vertical chases. So you don't want air in those chases moving around. So by sealing both sides of that top plate, we don't have chance for air to get out of that chase and go around. The next thing we want to look at is a cap plate. In theory, a cap plate doubles the vertical capacity of your SIP wall, which is great. It does that. But the problem is the vertical capacity of your SIP wall is very high to begin with. It's 2,000 pounds per linear foot. Almost all residential conditions and a lot of commercial conditions never reach 2,000 pounds per linear foot force, vertical force on the wall. So there's no reason to put a cap plate on to increase it from 2,000 to 4,000. Over all the buildings I've built, I very, very rarely use cap plates. And it was in apartment complexes that are 4 or 5 stories high. And I have these big meeting rooms down on the first floor with long span trusses that put a lot of load on that wall. And then you add the load of the floors above and you get above your 2,000. In that case, I would use a cap plate, but very rarely, because it creates thermal bridging, and it also creates cost and time. I keep talking about this sealant we put in. Sealant is not glue. If you think about it as glue, you're going to put it on incorrectly. Now, these people thought this sealant was glue, and they're thinking they're gluing these panels together. So they just put a whole bunch on haphazardly to glue it together. This does nothing. The sealant's supposed to stop air, and if you do it like this with gaps and everything, air will get right through it. The correct way to apply sealant is a nice big bead all the way around your panel so that when your connection comes together, air can't get through that connection anywhere. So when we start to build our building, we always start at a corner. So we stand one panel up, and then we take a second panel, stand it up, and we slide it to the first one. But before we slide it, we want to put this bead of sealant all the way up the face of the first panel. No gaps and a real big thick bead of sealant. So when we push those together, that sealant gets squished out, fills up all the little holes, and tightens up that joint. Now we want to put in our SIP screws, which are typically 12 inches on center, as we go. We don't want to put in a couple screws and say, oh, I'll come back later and do that, finish that up, send some cheap worker back to do it. No, because again, we want to make sure we seal that up tight so that sealant doesn't rubberize before we get it tight. So we want to make sure, again, every one of our connections, we want to make sure we tighten it up and finish it as we go. Now you notice on this particular system, we have very little thermal bridging in the corner. We have 1 2x that spans inside to outside. On conventional framing, you would have at least 2, probably 4 or 5 in that corner. So this reduces the thermal bridging over conventional framing by a lot. So you're building the building and you put up the first panel, and then you have to put up the second panel. So how do you connect those together? Well, we use a spline, and this is the best spline to use. It's the cheapest. It's the easiest to install. They call it a block spline. Some companies call it a super spline. But you notice there's no thermal bridging on this spline. The foam in the panels has been recessed 1.5 inches to allow this 3-inch wide spline to sit in there. We put our sealant, our 2 beads of sealant on either side, put it in there, use our ring shank nails to put it together. Excuse me. The second spline is called an I spline. It uses a WI section. And we use this when you have strong transverse loads, loads that are coming into the panel from the skin, say like on a roof or a floor, somebody walking on a floor. It increases the transverse capacity of the panel quite a bit. And it goes in just like the other spline, put your sealant in, and again, there's no line directly through the panel. Any air movement would have to go through the panel, around the spline, past all that sealant, back around and back out that hole. So it's minimal thermal bridging. I can't say that about this spline. This is a 4x or larger post. These splines are used when you have large point loads coming into the wall, say 4, 5, 10, 12,000 pounds, and you need something to take that load and disperse it into the wall. So you need to have the lumber in there to take that. Unfortunately, structurally, we need it, but environmentally, we don't want it. Large thermal bridging, so we try to not use these when we don't have to, but sometimes you can't avoid it. There is a better way, though. There is another spline called a thermally broken 2x. Now you notice here, again, we have no thermal bridging, but we do have more material to set our big beam on. We have 2 2x4s to rest it on. And that's a lot of load. Now it won't take all load. You still get a beam or a girder truss coming in that this won't handle it. But for medium-sized loads, this is a great spline. But you would only use it where you need the point loads. You won't want to use it at every connection. Now the next spline I want to talk about is the double lumber spline. And there's only one thing you need to know about the double lumber spline. Don't ever, ever use it. And I'll tell you why. You'll notice here that there is a line from the inside to the outside of the building, a straight line. So you always want to avoid that. And in this case, we have 2 pieces of 2x that are nailed together with smooth shank 16 penny nails. So what happens is during the seasonal temperature changes, all materials want to expand and contract. So when the sips contract, they actually pull this apart. And the only thing stopping it are those smooth shank 16D nails. Now they have very little pull out. I mean, you can pull those out with a claw hammer. So when this force hits it, it just pulls that joint apart. What that does is it allows your inside air to leak outside. So you have totally destroyed the infiltration part of your environmental envelope, because now you've got air movement through that wall. But what's worse is if you live in a cold climate, that warm, moist air will go through that wall, hit the cold air outside, and condensate. So now you have water in your joint, and the water will cause rot and mildew and mold, and this joint will eventually fail. I mean, the wood will decay and it will fail. So you don't use this because, you know, you get your air movement. But there's another reason. Your R value. Now, typically, double lumber splines are said to be spaced at 48 inches on center. Okay, so you have 2 2x at 48 inches on center. Well, that's the same as 1 2x at 24 inches on center, which is the same as conventional framing. So now you've taken your R value from R23 back down to less than 17. So not only have you destroyed the infiltration part of your environmental envelope, you've destroyed the R value of your environmental envelope. And the third reason is that you take two 2x and you try to nail them together to make a 3-inch by 5.5 piece of lumber. It's not going to happen. 2x are warped, they're cupped, they're twisted. So you could work forever to try to get two 2x to line up perfectly, and you can't do it. So now you have one sip on one 2x, one sip on another 2x, and those 2x aren't perfectly lined up. So now your nice, smooth, straight wall has got bumps in it, and you can see those bumps. So all around, you do not want to use a double lumber spline.
Brian,
Yes.
Can we specify what type of spline we want from each manufacturer, or do some come with certain splines?
Most manufacturers will provide you at least the box spline or the eye spline.
Okay.
The wood splines are on your own. The double 2x thermally broken spline, I believe, is a proprietary spline. So only one or two manufacturers might be able to supply that with you.
Okay.
But
Great.
the engineer is the one who should specify what type of splines go where.
Yeah. Great. Thanks.
Okay. So we'll switch over to headers. Now, headers is that structural element that goes over an opening. So any loads above the opening can go find its way past the opening into the outside. SIPs have three types of headers. One is called a panel header, and it's nothing more than a hole in the wall. 1.5 inches of foam is removed around the hole, and you just put bucks or 2x in that hole. You put your sealant in, of course. And structurally speaking, this creates a box beam. We've got our bottom flange and our top flange, which are our 2x here. And our web or our box section is the OSB. And this is a structurally sound beam. And these can hold quite a bit of load, but not a whole bunch, but enough for most residential openings use these type of headers. 90 to 95% of residential openings are panel headers, which is great because there's no thermal bridging and they're real inexpensive. If you can't use a panel header, say over a garage door or a sliding glass door, you have to go to something else. And the next step up is an insulated header. Now, this consists of a couple pieces of LVL with foam in between. Now, you also notice there's still not a lot of thermal bridging here, but this really increases the capacity of the header. So now you could go wider. You can go 8 or 10 or 12 feet wide, depending on the load, and still not have that thermal bridging, which again, I can't say about this one. Sometimes insulated headers just aren't strong enough. You get an 18-foot high garage door, you get a lot of load on it, point loads. You have to go to a solid wood header. Now it can be a 6x10, 6x12, it can be LVLs, it can be like here, a glulam beam. They're unlimited in height based on your geometry, so they can hold any amount, but they are not good in the environmental envelope. So we try to avoid them. Try to use the insulated header wherever possible, but sometimes you have to go with the solid header.
Yeah.
So let's see how
Brian,
these headers.
Brian, one question that came up is when you order SIPs for a project, does the order come with directions for correct connections that eliminate thermal bridging, or is that some training you have to do offsite?
A good set of engineering drawings will have all the details in it.
Great.
It won't rely on the manufacturer's details. The manufacturer's details are good in a lot of cases and bad in a lot of cases, and they're pretty generic. So the details on the engineering set of plans are very specific to what you're doing. So those would be there. And then when you get your plans done, they go to the manufacturer. They do shop drawings.
Yeah.
And they come back, and the engineer should look at those and make sure that the right headers are where there are on the plans.
Great. I have a quick follow-up header question on the insulated header. How does the load from above get transferred to the LVLs sandwiched between the OSB? It's from the top. Nails or top
Nails.
plate?
The engineer should specify a nail pattern for any insulated header.
Okay.
It depends on how much load there is. So sometimes you need an insulated header because it's slightly bigger than a panel header. You have just a little bit more load. You don't need a lot of nails to transfer that, but sometimes you need it and it's almost fully loaded and you need more nails. So it's up to the engineer to specify a nail pattern through the skin into the LVL. And it's the same with the solid wood header. Same exact process. So let's look at how these work in a wall. So a simple panel header is easy. You got a hole in the wall, you put in your 2x, put in your sealant, nail in your 2x. You're done. Very simple, very inexpensive. Doors work the same way. But now if you need a header, you go to a door. There's two ways of putting in a header over a door. You can put it at the top of the wall, or you can put it at the top of the opening. Now, the reason you would put it at the top of the wall is that allows you to build the walls and come back later and just drop in the headers. So the building of the walls goes very fast. Now, anytime you have a header, you need something to take the load from the header down to the floor below. And those are called trimmers. So our two trimmer studs go in, but you notice they're not at the edge of the panel. They're set back 1.5 inches. That allows us to put our regular splines in. So we're not using that double lumber spline. We're using a regular spline that crosses that joint. We do have to buck out inside, which gives us a little more thermal bridging that we don't like, but it's something we have to do. And then later on, they can come in and drop that header in from the top. One thing you notice here is there's no king studs. King studs do nothing in a SIP wall. Now, the exception is big commercial buildings where you have huge openings, have a lot of load coming across the top. But the fact is, SIPs are a stress skin panel, meaning the load that hits above the opening goes through the skin across the spline and to the skin of the next panel. And from there, it can go up and down. Now, with conventional framing, that force goes out across the framing, gets to the edge of the opening, and there's no place for it to go. So you need those king studs to take that force up and down. But in SIP construction, the king stud is not as stiff as a stiff SIP wall. And stress goes to the stiffer member. So even if you put a king stud in there, the stress will never find it. In fact, if I was a piece of wood, I would love to spend my life as a king stud in a SIP wall because I would have no stress in my life. But there's a better way of doing this type of header. And that's to bring it in as a low header. This is better for your environmental envelope, but it takes longer to build in the field because you have to sort of stop right here and do the header. In this case, you put your splines at the top of the wall and you slide your header up underneath. Now the bucks of your opening become your trimmers. So we don't have extra trimmers and bucks. We just have a buck trimmer combination. So that definitely reduces your thermal bridging because you don't have that extra piece of lumber. And again, there's no king studs. All king studs do is allow thermal bridging. They don't increase any strength whatsoever. With windows, it's very much like a door with a high header. You put in your trimmer studs, you put in your splines high and low, then later on they can come in and drop in their header, and then they can nail it all off. So it's very similar. Trying to put the header underneath at the top of the window opening is a lot more difficult construction. So most windows are done this way. And again, you will notice there's no king studs. So now we've built our entire building and we want to go up. We want to do a 2-story building. So how do we do that? Well, in conventional framing, they use what's called a belly band. They take their floor framing and they set it on top of the bottom wall. And then they take a rim joist and put it around, and they take their floor, whether it's TJIs or trusses or lumber, whatever they're using, and they put that in against that belly band, put their sheathing on top, and then put a wall on top. Now, the problem is you get thermal bridging. That rim joist collects a lot of energy, and it will put it to the floor joists that are touching it and go into the building. No matter how much insulation you do here, you can't stop that thermal bridging. It's a little harder to insulate. You can spray it or you can put bat in there, but still your insulation is not that good. The other problem is structural. You have to get all the lateral load from that wall and from that diaphragm up at the top down through that system to the wall below, which is going to resist it. You do that with hardware, A35 clips, things like that. Hardware moves. You put it in, the nails aren't exactly the size of the hole. The hole's a little bigger. So they move. And what that does is it creates problems with your exterior finish. You start getting cracking. You'll notice on a lot of apartment complexes where that belly band is, the architect has put some sort of feature to avoid seeing that cracking and that movement. In the SIP world, we don't do it that way. What we do is we hang our floor system from the top plate of our SIP. So we take our SIP all the way up to the bottom of the floor sheathing. Then we hang our floor system, put our sheathing on so it goes all the way to the outside of the wall. And then we can attach it all together using 16-penny nails. Now our shear is transferred directly through shear in those 16-penny nails from the top wall through the diaphragm, which is the plywood, down into the wall below. So now we don't have any movement. We don't have to put all that hardware in. The building goes up much faster and it reduces a lot of that thermal bridging. Because now all we have is thermal bridging through the two plates and through our 3/4 or 1 1/8 inch plywood. Again, make sure we seal all those joints so we don't get any air movement. But there's a better way than this SIP platform framing, and it's balloon framing. Now this has the advantage that there is no thermal bridging. So except for the screws, which are very, very minor, you get no way for energy to get through that wall. The other advantage is you can put that ledger anywhere elevation wise. So it can go 9'4", 10'7.5", doesn't really matter. With the previous example, to be economically sensible, you want the lower walls to be a standard SIP height, 8, 9, 10, 12, 14 feet. So you're kind of limited on where your floor height is and what your head height is. So it's kind of a step function. You don't have to, you can cut off those panels, but that's expensive. So you really want to try to avoid that. This allows you to put your floor anywhere you want. So now let's move up to the roof. Of course, we all want to use SIP roofs, but that's not always possible. You get roofs these days that have a ton of hips, a bunch of valleys, dormers, Dutch gables, all sorts of things going on. And with SIPs, they have to bear on something. So your substructure becomes expensive and hard to frame. Trusses, on the other hand, can do all that real simply. So how do we marry the truss with the qualities of the SIP wall? We do that by using spray insulation. Now here we can use spray insulation. It will go in and expand, and it will fill in all the crevices so we don't have any air movement. But we can also put in the spray insulation so it is deeper than the top quarter of our truss. Now that eliminates our thermal bridging. So our R value goes way up. So now we have the two pieces of things we are really looking for. We have stopped infiltration and we have a high R value. But if we want to use a SIP roof, it goes together like this. We have our SIP wall, we put our roof in at some angle, we screw it in, and we end up with that little triangle of space right there. So what are we going to do with that little triangle of space? We're going to fill it with foam. The problem is that screw right there, that big SIP screw, is in bending. Anytime a screw goes through air, it goes into bending. So a better solution is to rake the top of the wall. Put our sealant on, put our screw in, we've eliminated the structural problems. Some people say it's more expensive because the companies will charge you to, bevel the top of their SIP wall, 3 feet or something, a linear foot. Not real expensive, but some people say it is. It's well worth having the finished product like this. So our buildings are done. So now let's move to accessories. These are what things you can put on your building after it's done to try to help the environmental envelope. The first one is SIP tape. Now, SIP tape is designed to stop air movement through the joints, the vertical joints, your roof to wall joint, ridge joint, all those joints. But you want to put it on the pressure side, okay? Because when your building pressurizes and the wind is pushed against it, it's pushing the tape against the SIP, not trying to pull it away. And by doing that, it makes it very hard for the air to get through that and through the wall. It's cheap. It's not very expensive. So it's cheap insurance, and I highly recommend it. And the SIP manufacturers also highly recommend it. Another one people look at is house wrap. Now, house wrap is designed to stop air and water from moving through the wall, water from getting to the outside of the wall. I don't recommend it because the house wrap is on the outside of the wall. So as far as stopping air, if air does get through the SIP wall, which it shouldn't, but let's say it does get through that SIP wall, it's pushing against that house wrap, which pushes it away from the wall and allows the air to escape. Now, it's not a perfect world. So out in the field, things happen. Somebody forgets to put sealant somewhere, or things just don't line up and there's a little gap. That's where the SIP tape comes in and these accessories to try to fill those up so that in a non-perfect world, we might get a perfect building. So to wrap it up, there are things you should do. You should use sealant generously, and you should use it at all your places, and you should button up your connections as soon as you put it there. And use the SIP tape when you're done. It's a cheap insurance and it helps a lot. Things you should not do is use a double lumber spline. Never, ever use a double lumber spline. Cap plates, king studs, use them if they are required by the calculations. Don't use them because it makes you feel better. Oh, we need lumber in here. Let's put some king studs in. It makes me feel better. Don't do that. Calculate it. See if it's required. And try not to use the belly band construction. Try to hang your hangers inside. So if you do all this, I'm pretty sure you can have a very environmentally attractive building. Thank you.
Brian, first question, have you seen people use fluid applied weather resistant barrier on SIP buildings, and what's your thoughts there?
I have. You get those cans of liquid rubber, whatever they're called. You see them on late night advertising. I've seen them use that instead of the SIP tape. As far as inside the wall, some people use an expansion foam. If you use a sealant right, it would work, but expansion foam works too.
Yeah.
That was the question.
Sure. And then a lot of questions on earthquake, seismic, and hurricane resistance of SIP panels.
Okay, this presentation was about energy, but I'll answer that question anyway.
No, thank you.
SIPs are light. Okay, an earthquake, F equals MA. So the mass of the object in the earthquake is part of the equation. The higher the mass, the more force. Okay, and then the earthquake's a constant, whatever the earthquake is. So because SIPs are lighter, they have to resist less force. But because SIPs are much stronger than stick, they don't have to be as strong because they have to resist less force. So the answer is SIPs are great in earthquake situations. They're basically made for it.
Great, thank you. 2-hour firewall assemblies between like a townhome type, is there a solution for SIPs?
There's solutions out there, but none of them have been rated. So you don't have documentation on them.
Right.
I would love to get SIP companies to do a 2-hour test and also redo the 1-hour test. Right now, the 1-hour test calls for a couple layers of drywall. I believe that one layer would probably work for a 1-hour test, but it hasn't been tested, so nobody really knows. So I would love the SIP company to figure out what a 2-hour rated wall would be. It may just be an extra layer of drywall, or
Yeah.
it may be clips, it may be something else. But the
Yeah.
failure mode in a fire is not burning. It's energy
Oh.
getting through to the EPS, EPS, and causing it to back away from the skin. And then the skin will buckle. So that's the failure mode. It's not burning itself. So we have to figure out a way to keep the energy from getting in there. There's coatings out there that are available. Of course, drywall has a lot of water in it. It takes a lot of energy to convert that to steam to get through. So I would love to see that, but right now there's not a standard 2-hour firewall.
Okay. You mentioned 5/8 and 3/4 OSB skins on the outside. When is it appropriate to look at using those?
5/8 I use a lot in restaurants because they use what's called a black space above their decorative area. So about 10 feet and above, they just paint everything black.
Yeah.
So they don't want to put drywall up there. They don't want to finish the SIPs at all. But according to code, you need like 0.47 inches of protection over the EPS. Well, 7/16 of an inch is 0.43 or something. Doesn't quite make it. So on restaurants or places where they're not going to finish the inside, I always spec 5/8 because then it meets that code for the plastic insulation part.
That's great.
Now 3/4 you would use if you have high winds and you need more transverse load capacity.
Right. Great. Here's a great question because I know the answer to this. Brian, do you have any experience with SIP roofs over ICF construction? I think that is kind of how your house is, right?
Well, not really. I have ICF mine is a multi-level, has ICF for underground, and some of that comes out of ground. Then I have SIPs and I have a SIP roof. Excuse me. But I do have a lot of experience with ICF walls and SIP roof. The Catholic Church does that for one great reason. Bullets. They don't want bullets. And I'm sorry, SIPs just don't stop bullets. So they use ICF walls and they put a SIP roof. It's very simple because on top of the ICF wall, you put a nailer. You put in anchor bolts and you put in basically a sill plate on top of your ICF wall. And then you can put your SIP wall on top or your SIP roof on top and screw it in just like you normally would to any wood wall.
Great. Brian, what about SIP tape on the inside of the structure and house wrap on the outside?
You can do that. If you were careful doing your joints, the SIP tape is just taking care of those few little places where it didn't quite work. So with the SIP tape and proper joint construction, you shouldn't have any air movement. So the house wrap won't help with the air. The house wrap is not really good with water because it's plastic. And when you put nails or staples through it, it's plastic. It helps a lot, but if water gets where those nail holes are, it will get through. The type D building paper that I like has asphalt in it. So when you put it on and you put a nail through it, it's self-healing. It heals up around that nail, so you won't get water through. And the type D house paper is cheaper than house wrap and faster to install. You don't have to tape it and all that sort of thing. So I really don't recommend the house wrap. But if you want to use it, that's fine. I mean, house wrap's a good material.
Great. Brian, what about how to seal electrical boxes in a SIP panel?
Well, you don't really have to seal the electrical boxes because the chases are sealed. Using the two beads at the top of the wall and around everywhere, there's nowhere for the air that gets through an electrical box to go because it's
Right,
all
because-
sealed in.
Yeah, it's all in the EPS, right?
It's all there. It can't get out to the outside.
Mhm.
Now, some people use spray foam to hold the electrical box
Mhm.
tight in the foam because there's no stud. When you put them in, there's no stud for the electrical box.
Mhm.
So you use the electrical box with the little tab on one side, you screw it in, and it's still kind of flimsy. So
Mhm.
some people throw some spray foam in there to tighten that up.
Yeah. I think one area, Brian, we saw in our apartments that are SIP is on the back-to-back kitchens, you're putting an outlet in each side of the wall for the kitchen layout. And then we had to do some air sealing behind those.
Okay,
outlets.
that's where the architect needs to come in,
Yeah,
and move those electrical boxes.
yeah,
Even in stick framing, SIP framing, whatever, you never want two electrical boxes back to back.
right,
The mising wall. You want them moved apart.
right.
So if nothing more, put one on the right side of the stud and one on the left side of the stud.
Right.
For one reason, you've got that air transfer. You also get sound transfer through there. And if there's ever a spark or anything and one side gets hot, it will transfer to the other side.
Right.
So you want to not put electrical boxes back to back.
Great. Question on this person is constructing a single slope cathedral ceiling. Should I-joist rafters be hung from the cap plate or similar to balloon framing example, have rim board inboard of SIPs to hang joists? What's your favorite method there?
Well, I heard joists a couple times. My favorite method is to use a SIP roof.
I think that's what there's, I think that's what they're saying. Todd,
Well-
maybe you want to clarify your question.
Yeah, because SIPs can span. I mean, my house, my roof, the SIP spans 24 feet.
Mhm.
Yeah, I live in Phoenix. I don't get any snow. But my preferred method would be to put beams at 16 or 12 or 18 foot on center and span the panels between beams. If you can't span the panel from wall to wall,
Mhm.
if it's wider than 18 feet, say.
Yeah, what he's got, Brian, he just clarified it. Thank you, Todd. Yes, it's a SIP roof, but I-joists are supporting the SIPs and the clear span is 22 feet. I assume he would have them 8 foot on center then. He's just supporting the.
No, when he says the I-joists are supporting the roof, it sounds to me like it's an I-type spline inside the roof panel. So every
Ottawa,
4
Canada.
feet, he's got joists, I-joists.
Yeah,
And then in which case, if the
Snow
wall
load.
stops and the roof goes over it, just set the roof on top. If the roof butts into the wall, then you're going to need a ledger to take the vertical load. And you're going to need to put SIP screws in from the outside into the butt of the roof to take the horizontal load.
fantastic. And Todd, we'll go back to Brian's contact information, and that might be worth a quick call to him on your question. But snow load area up in Ottawa, Canada. Senators look like they might be good this year, Todd. I don't know. Could be the year. One question, who typically is doing the installation of SIPs? Can it be done by framers or do you need specialized crews?
It can be done by framers. Now, a lot of companies, Muris I know does it, Premier does it. They'll send people out to train the actual framers that whoever got the job who don't know SIPs.
Yeah.
They're not very difficult. There's also crews that travel around the country that work for contractors to install the SIPs.
Yeah.
The pictures I showed you about the mastic, the poor job was done by just framers. The good job was done by one of these crews that travels around the country.
Got it.
So, I mean, the crews are usually better at it. So if you don't have good supervision, then the crews are better. But if you have somebody or hire a very good SIP person to watch everybody and train them properly, then any framing crew can do it.
Yeah, and I would add that both SIPA and EBA have the SIP Certified Master Installer Program in our learning management systems. And that's a great place to start if you want to learn more. Brian, do you know if SIPs are a good strategy to achieve FIAS certification or passive house?
Yeah, anytime you need to stop energy from going not where you want it. Now, a passive house will have windows on the south or north side, wherever it's located, to allow energy in during the winter, and then large overhangs to stop it during the summer. So yes, because you're using natural energy and it's not overly abundant, a SIP structure is really great for that.
Yeah, it's a Yeti cooler for your house, and that's kind of what FIAS would like you to build anyway, right?
Yeah, you're basically living in a styrofoam ice chest.
That's right. Brian, can you share your, I don't know if you want to go back to the title slide and share your email address? Lots of requests for contacting you. So
I don't even think I put it on here.
I think you had it on the home slide, didn't you?
No.
Otherwise, will you type it in the chat for us?
Sure,
Right.
I knew where chat was.
I can type it. What's your email, Brian?
It is Brian, B-R-I-A-N. The letter V as in Victor.
Yep.
At Wright, W-R-I-G-H-T, engineers, engineers.com.
Brian V at wrightengineers.com, everyone. Brian, I want to thank you so much for joining us today. This presentation will be available in the EBA Academy, our learning management software, and we will have it in the Hoover app throughout the upcoming summit in Scottsdale. Brian, thank you again.
Thank you.